Hello guys, in this video I'm going to explain what are machine learning models compared to AI, compared to deep learning, compared to LLMs, compared to everything, right? I'm going to show you here different types of machine learning models. I'm also going to explain here what is an LLM, what is AI, what does that mean exactly, and that's pretty much what we're going to go over in this video today, right? My name is Shot, also called Stefan Jean-Claude. I've been an AI programmer for the past 7 years. I've been involved in data, analytics, automation, machine learning, AI, statistics, math, all those things for the past 7 years. So I'll be your guide through this process. All right, let's get straight into it. The word car is like the word AI. All these things here are cars. All these things here, except for this little thing right here, technically is AI, but programming is a part of AI, right? So all these things, NLP, computer vision, image generation, video generation, LLM, robotics, deep learning, machine learning, statistical models, statistics, math, all of these things are under the umbrella word of AI. AI means all of this. Deep learning is AI. Math is AI. Statistics is AI. Robotics is AI. It's all part of the subject, okay? A Jeep is a car. Whatever this is a car. I think this is McLaren, is a car. That's a Honda Civic, I believe, is a car. This is a Toyota SUV, is also considered a car, right? They're all cars. They all function differently. They all have different, like this one's really fast, but it's not the newest model, right? New doesn't always mean faster, and new doesn't always mean better. New just means different, especially in the AI space. New means different. Some things from the old might be better, but some things from the old, like the new model might have, like a new model, like a car model might be better in some ways, but not every single way, right? The older model might be just fine, and the older model might be better at certain things compared to the new model. Okay, people think new always means better. That's not what that means, especially in the AI space. A new model does not always mean better in every aspect, right? Cool. Because, for example, a football player, how do you compare two football players? How is one better than the other? One might be faster, one might be stronger. They're both better, right? Let's say I have like a athlete that's been around for 20 years, an athlete that just joined the field. He's new, he's fresh. Oh, he's better than the last guy. In what sense, right? Like, you gotta understand what better means in these situations. Is he faster? Is he stronger? This guy might be stronger, but this new guy might be faster and more intelligent, like on the field, and that might score more points, hence him being better, but he's not stronger, right? You know what I'm saying? So that's kind of like the idea I want you guys to get into your brains, okay? So let's just break this down. What is AI? I mean, this is like a quick history. AI has been around since the 1950s, 60s, or 70s. People argue on when exactly it was created. It was created around the 1950s, 60s, and 70s, okay? People care about it's been around. The only reason why you didn't hear about it is because it didn't talk. Once it talked, then it went viral and everyone freaked out and all these movies came out, and here we are today, right? Cool. Now, statistical model, statistics and mathematics. Statistics and mathematics is the original AI. All these AI models use statistics and use mathematics. That is their core, the core of AI, right? The mother and father of AI is statistical modeling, okay? Statistics and mathematics. Now, when programming met statistics and they got married and they had kids, the kid was machine learning, okay? So machine learning is the child of statistical modeling, which involves just writing pencil and paper, or maybe they have little computer software that like they can do statistics on and stuff like that. But when that was combined with programming, right, programming things, that's what created machine learning models, okay? I'm gonna give a bunch of examples of machine learning models here for you guys in a bit, but hold your horses, okay? Then, after a couple years, machine learning models, then we had deep learning models, which involves neural networks, okay? I mean, deep learning models are models that use neural networks. They are technically smarter and better at handling things than the old series, but these guys are super specialized. They didn't handle a lot of data very well. These guys can handle a lot of data, right? And they can do a lot more complicated tasks. But there's a con to this. The con of deep learning models is they require a lot of data. I mean, a lot of data to work properly. If you have a small data set, they don't work very well. But if you have a small data set and you need a quick answer, machine learning models are your go-to. This is just overkill, right? It's like if you want to kill an ant, you get a car to kill the ant versus just squishing it with your finger, right? Same concept, you know. If you want to cook some food, you don't get a bomb and blow up the food. You get a little, you cook it on the stove, right? It's overkill. Sometimes deep learning models can be overkill for your situation, okay? So Let's go with, so yeah, and then after that, deep learning broke into a bunch of different subcategories, okay? We have NLP, natural language processing, right? And the best way to understand what this is it later became LLMs, TTS, STT models, LLMs, ChatGPT, Claude, Gemini, right? That's what blew up the world. This right here is what blew up the world. NLP models, the things that came before it, RNNs, GRUs, LSTMs. This is the original NLP, that's like the older brother of LLMs. If LLMs is the new kid in town, he's the young little kid that's super smart. His older brother that existed before him was NLP, right? So, and TTS stands for text to speech. So the models that can say what it sees, what it reads, like it reads things out loud, and models that can hear what you say and turn it into text, that's all within the category of NLP models that came out later, okay? So LLMs, TTS, and STT came out after NLP models were created. Computer vision, which is pretty much, just the computer understanding what it sees, understanding pictures, CNNs essentially is what that is. And then you have image generation, video generation came out of that study as well. Then we have robotics. The closest thing we have in our hands of AI robotics is things like a lot of toys have it, Tesla cars have it, things of that kind of nature have it. Video games also have use robotics, and also like automation systems like UiPath, things like that pretty much use the concept of robotics. A lot of automation systems, right? That's the best way to explain that category. And there's a lot of things in itself that kind of goes on, like reinforcement learning is involved with this as well. Video game characters is involved in this as well. So keep that in mind. This one's very broad, but this is not talked about well enough yet because the use cases are very much more towards flashy things, not necessary things, and they're not going to take jobs. Once Tesla goes into its next phase as a company, then people are going to freak out about this area here. That's why I tell you guys the next explosion of AI is robotics. So if you want to be ahead of the game, you need to learn robotics, okay? And that's what I recommend people as well to get involved with that, okay? So now, what is going on? So now we're going to do machine learning models, okay? So machine learning models are pretty much statistics and programming coming together, basic statistics, right? So we have linear regression. Linear regression is a supervised model, okay? That means you have to tell it labels. Essentially, it's predicting the next value. So let's say we have this line, you want to guess the next point in that line. That's all linear regression is. You usually see it a lot in things like house pricing, like when you're pricing homes, guessing the prices over the years, or stock market prices. The original stock market prices, like AI models or whatever, were linear regression models, right? Now, they only are good at handling linear data. If the data is not linear, then it doesn't work very well, right? Which is a problem that it had. But it works really well, and it's easy to understand if you have small data and data that follows this pattern, okay? Then we have logistic regression. This is usually good for, it's like binary, right? Picking one thing or the other, black or right, red or blue, left or right, boy or girl, dead or alive, right? Like these words are very binary. So logistic regression is really good at handling things like this, right? So it's kind of like everything on the left of this is one thing, everything on the right of this is the other thing. It's better at linear regression of handling these kind of tasks, okay? Next we have decision trees. This is what helped create LLMs to this day. LLMs, these super fancy models, the core of them is a mixture of linear regression, a mixture of logistic regression, and a mixture of decision trees. So let's say a decision tree essentially is pretty much deciding something, like your thought process of deciding something, and the chances of choosing one thing over another based on the situation. So let's say you want to play tennis today, right? You go outside. If it's sunny, okay, cool. It's a higher chance I might go play tennis if it's sunny outside. But if it's high humidity, I can't play tennis. It's too humid. But if the humidity is low, I'm gonna go play tennis. That whole was a decision tree, right? Then let's say it's cloudy outside, not hot, not super cold, not windy, whatever. Super high chance I'm gonna go play tennis, right? But then let's say it's raining. It's like, okay, my chance of going out to play tennis is kind of low. It's pretty low now. And if it's windy with rain, maybe it's not that, maybe the rain's not that bad, and it'll be a cooling effect. The rain, usually it hits the side of the field, so it doesn't actually hit me, so I might still go play tennis, but it's a lower chance. And if it's strong winds, probably a hurricane coming, I'm not going to play tennis. That's a decision tree, and that's a whole statistical model. Each one of these points has a percentage chance that it will happen based on the thing before it, okay? So the sun, right, might make it a 60% chance that you will not go out to play tennis, but if it's sun and humidity, right, like it's that kind of process, right? Each of these has a percentage that affects the other one of what will happen, okay? It's like a chain reaction, domino effect is the best way to explain it. Next, we have random forest. Now, random forest is pretty much like our voting system for America, right? Or what's it called? When you vote for something, yeah, like a voting system. Essentially, it's a voting system, right? Each person is his own decision tree, and based on their mood or whatever, or the information they hear is going to affect like what they decide on, and they all agree together. Now, imagine this voting system was a bunch of yous. Imagine 6 Stephans. Each of us are the same person, but based on the situation or the data or the time of day, I might make a different decision, right? If I'm hungry, I might make a different decision. If I'm full, if it's nighttime versus daytime, I'll make a different decision. If I see red before talking to you versus a TV show before talking to you, I might respond differently. So imagine 6 Stephans, and you give us the same information at different times, and we all vote on what the best thing to do is. That's a random forest in a nutshell, okay? Pretty much, it's a bunch of decision trees. A random forest is multiple decision trees working together. Gradient boosting. The best way to explain gradient boosting is imagine, okay, this is gonna sound, no, I'm gonna think of a better one. So imagine you saw me play with this yo-yo, right? So imagine you saw me do something like, so the goal, is this even working properly? So imagine the goal is to just have it swing left and right. Cool? That's the goal action. Now, let's say there's 3 people involved, and the 3 people are the same person. Let's say there's 3 Stephans. Stefan 1 grabs the yo-yo and he goes like this. Oh snap, right? He just keeps throwing it, right? And this is wrong. How wrong is it? Maybe it's like 90% wrong. The action of throwing is correct, but he throws it too hard, right? And then also he needs to dodge and stuff like that. So yeah. Then second Stefan watches first Stefan do this constantly. So now second Stefan comes and he understands that the goal is to just do this. So it's like, all right, how do I get to this from what the heck the guy before me was doing? So he saw what the first person was doing, which is first Stefan. Now second Stefan's gonna try doing this, right? Second Stefan's gonna try doing this, which is a lot closer, but the technique is a little rough. Second Stefan's throwing down versus throwing at an arc, right? Now third Stefan is watching second Stefan do this, right? And third Stefan's like, wow, the goal is to do this. The second Stefan is doing this. He's pretty close. Let me try something different. So third Stefan comes. Third Stefan now understands to throw with an arc, and he does the activity that is required, right? That's what gradient boosting is. It's learning off the previous model's mistakes, essentially. That's it in a nutshell, okay? Support vector machine. It's pretty much a better version of linear regression and a better version of logistic regression. But it's not better. You want to use this when you have a lot of different dimensions. A dimension in this scenario, I have a yo-yo, right? Little yo-yo. This yo-yo has a million dimensions, but I'm gonna focus on just 5 of these dimensions. It's blue, right? It's light blue. It has a string. It has a blue dice. It's round. It's light, and it's smooth. Okay, it's pretty smooth. Cool. Those are all dimensions. The qualities of this thing are all dimensions. And then we can even add another one that this is a square or it's a cube. We can even add on, it has dots on it for representing the numbers of the dice. We can add on the string color. We can add on the center color. That's almost like 10 features, aka 10 vectors, aka 10 dimensions, right? So that's just the idea of what a dimension is per se. And pretty much when things have a high amount of dimensions, when it's 3 or higher, pretty much if it's higher than 2, but if it's 3 or higher dimensions, then you might want to use an SVM to handle the situation, okay? Linear regression usually is like 2 different dimensions that you're kind of comparing. Like you're comparing one dimension to another dimension, like height versus weight. It's like there's 2 dimensions, but you're comparing those 2 dimensions on the line. That's for linear regression, which is really good for linear regression. Support SVMs might be overkill for that kind of situation. Logistic regression is kind of like so if something is heavy or light, right? That's better for logistic regression, right? And then, but SVMs, it's more like, okay, if I have 3 groups of people which group is the fastest, right? That's kind of what SVM is better at finding, right? Things like that. Just to give you an example. Now we have K, and by the way, all of these are supervised learning models, okay? This is the last supervised learning model. Supervised learning model means you tell the model what the labels are. Like you tell it, like, oh, I have a yo-yo that's blue. You tell it there's a center core that's gold, right? You tell it that there's a dice. You tell it there's a string. You tell it the categories and the things that's going on. That's what supervised learning means. You have to label your data. You can't just give it to it without labeling it first. K nearest neighbors is pretty much you tell it two groups. And when you add a new data point, it has to figure out which group does that data point, but that new one belong to. Does it belong to this one? Does it belong to this one? And it uses the distance formula essentially to kind of figure out which group does a new thing belong to, right? So if I have a water bottle, if I have a pill bottle, right? Let's say these are two different groups, and then I pull up my yo-yo. Which group is it gonna go to? Is the yo-yo gonna go to? Because this is also made of plastic-ish, right? Is it closer to being a bottle, or is it closer to being a pill bottle, right? I would say it's closer to being a pill bottle just because how thick it is. The color is also closer, and just how smooth it is, right? It's a lot of ridges, and also the size, right? Those qualities would make this closer to this guy, right? If I was trying to figure out which group does this one belong to, that's what a K nearest neighbor is. On a simple, this is. Moving on. Sorry guys, I'm trying not to over-explain. Now, this is an unsupervised model. This means you can give it data that has no labels. You can just give it a bunch of numbers that's organized. The numbers are organized at least, but you can give it a bunch of data that's not labeled properly or whatever, and it can figure out the categories kind of on its own, but it won't tell you what it thinks it is. You still have to go figure out what those labels are, but at the end of the day, the model can operate without you giving it a lot of information, which is really powerful, right? So it's pretty much the same thing as K nearest neighbors, but K means cluster. It's called K means clustering. K means clustering is unsupervised. K means clustering is very similar to KNN, but in the sense that you don't have to tell it the labels, right? And the way it operates too is a little bit different. That's pretty much how that operates. So pretty much it's kind of like if I were to show you the bottle without showing you the bottle, but I know how to, yeah, it's like feeling the bottle without looking at it, and I don't tell you what it is. You kind of have to figure out on your own, what is this? This is probably like a water bottle. Okay, then I give you this, and you're like, okay, what is this? This is probably, it sounds like pills. Maybe there's grapes inside. Okay, maybe there's a paper on this, is a wrapper. Okay, maybe there's maybe it's a picture of a dude doing backflips, right? And then you feel this, and you're like, okay, this feels like closer to the second thing I touched. That's how K-means clustering works, okay? Then we have hierarchical clustering, which is another unsupervised model. This is better used for things like social media networks or like chain of command, figuring out king, queen, son, daughter, family graphs is another way this is used a lot. But they're really bad at handling a lot of data. Usually it's good for small data sets that don't have a lot of features, okay? Usually you focus on like one feature when you're doing this particular thing, just one feature. But it's a nice visual to have when you have small data. PCA, Principal Component Analysis. Long story short, this model is used to reduce the amount of dimensions of a data set, right? So what that means is, if you're trying to figure out if the yo-yo is closer to being a water bottle or if the yo-yo is closer to being a pill bottle, there's a lot of things to consider. You have to consider weight, color, size, smoothness, aerodynamics, and then the list goes on. What PCA does is it focuses on as few things as possible to use to compare, right? Obviously, if I just focus on color and size, out of the three, these two are closely related. Just focus on color and size, right? That's what PCA kind of does. Instead of focusing on every little thing, what's inside of it, is your water, it's too much information, right? So that's what PCA does. Now, in all of these things I just touched, these are all machine learning models, okay? Now we're getting into deep learning, which are a bunch of neural network models, right? Deep learning is composed of neural network models. What's a neural network? It's these guys. So a feed-forward neural network is like the original neural network, the thing that blew up the world essentially. In the statistical world and mathematical world, this changed our lives, right? This is like nerd. This is like the nerdy stuff, right? Essentially, these guys are able to do the same thing as all the previous models, but a lot more efficient, and you can have more complex data, and you can have more, and you can have a lot more data. Remember, these guys are only good for small data, which you should use them for small data, right? Because if you give a neural network a small amount of data, it will not work very well, which is a problem people keep doing. People keep feeding these things just small little problems, and now they can't handle them very well because they're not made for that, right? So keep that in mind. So this is like the original neural network. Pretty much, best way to explain it is it's like your brain. It's like the closest thing to your brain. If your brain was turned into a mathematical equation, that's what a neural network is. Each of these points are equations essentially, right? Equations or programming equations or mathematical equations or the two combined. That's what a neural network is essentially, right? And fun fact, the best neural network architecture is probably this one. 3 layers. You just have one layer with a bunch. The hidden layer should just be a bunch of neurons. When you start doing this multi-layer stuff, it's actually shown to not be that efficient. You just kind of just need one layer that's just more neurons in it. But that's just a key tip from a experienced AI programmer. All right, next for CNNs. These guys changed the world for sure. They're able to recognize pictures and what's in a picture and pretty much it's able to tell you what's in a picture, right? So if you look at this example, it pretty much turns the image into a bunch of different things that the AI can understand. And you look at this guy right here, that's a forward-feeding neural network, as we saw earlier, as you can see. But convolutional layers is just chopping up the picture into different layers because most pictures are made of like pixels, and pixels make up an image, right? And the pixels return to an equation, but it's a whole thing. But long story short, these guys are used for recognizing images, what's in it, what objects are inside, what color is the image, stuff like that. That's what a CNN is really, really good at and what it's known for. And now we're reaching the NLP models, right? So the NLP model chain or the family of NLP models is the RNN, LSTM, and GRU. GRU is the best out of all of these guys. RNN is the worst, LSTM is the worst, and these guys, no one uses them anymore because LLMs exist. LLMs are the better version of these guys, right? You don't only use these guys if you don't have a lot of computing power with your PC. That's the only reason why you use these things, right? How they work is a little bit complex, but essentially it's able to go back. Like if you give it a sentence, it can look at the first word and the last word in the sentence. Like it can move around the sentence. And then let's say if I were to ask you a question, you can go back in time and check your notes to see what was there to answer the question, right? So it can go backwards, which was a really big deal in the AI world, okay? But these things are really good at anything involving language, talking, summarization, all that stuff. These guys can do it. It's just LLMs are the best. Transformers, this is what took over the world. ChatGPT's models are based on transformers. The T in ChatGPT stands for transformers. I'm pretty sure. Hold on. What does GPT stand for? What does GPT stand for? Transformer, yeah. So GPT, the T in GPT is transformer. So those models change the world, and pretty much it's a super advanced version. It's pretty much like an LLM. It's like LLM and Transformers are very close, but not the same thing. But Transformers came before LLMs. I know I didn't add it to that list earlier. It just didn't want to confuse you guys. It's just another chain down. So it's like NLP to Transformers and then to LLMs. That's like the history of how it happened, essentially. So yeah, and then they're just really good. They're good at generating, right? The G is for generative. So they're good at generating text. That's the difference between a transformer and a GPT model or LLM. LLMs generate text. Transformers understand the text. That's pretty much how they work differently. Okay, so transformer understands text, the meanings behind it, what's going on, what does it mean. It understands that the is a useless word, and it understands that the period means absolutely nothing, but that they're just done talking, right? It understands English, it understands the context and stuff like that, and it can learn these things, right? Then we have reinforcement learning. Reinforcement learning is in its own category. It's more towards the robotic side, right? Remember this graph earlier? Technically, the thing is, reinforcement learning can be done in NLP. It also can be done in computer vision. But you see it, they most use in robotics. So that's why I didn't put it here, because it will confuse you. All these guys here can use reinforcement learning. Reinforcement learning is the same way humans think. Oh, AI agents as well. I should have added AI agents. AI agents are a mixture of all these things combined. If the mother of LSTM, TTS, STT, like AI agents where you need all of these. You need LLMs, you need TTS, you need STT, you need image generation, you need video generation, you need robotics, you need all these things to have an agent, right? Now there are weaker agents that use just one of these, right? Or yeah, a weak agent just uses one of these things. The agent everyone's dreaming about, right? The agents people are trying to make right now are the ones that involve all these things combined, right? All these things combined right here is what an agent needs to do what we want it to do. It needs to be able to do tasks, right? It needs to be able to see what's going on. It needs to be able to generate images. It needs to be able to generate video. It needs to understand videos. It needs to say text. It needs to summarize text. It needs to do all these things, right? It needs to decide, oh, what do we do? And keep in mind, the reason why this is chain reaction, all these things use statistics. All these things right here use statistics. They're built off of statistics, okay? People don't realize that everything here I'm talking about is just a lot of statistics. Cool. Markov chain. Markov chain is the core statistical equation that builds all these things. But I will talk about statistics in the next video. Actually, I'm talking about statistics that build all these things so you can understand it on a deeper level, right? Because in this course, I focused on giving you the flashy, cool stuff first, simple to understand things first. So that way, now when we get to this point here in the series, you understand exactly what it is these things are, right? This video is part of a whole series teaching people like what AI is and how to use AI and how to code AI, right? That's the whole core of this series, and just to understand the deep how they work, right? So just to give that reference, if you didn't know that this was part of a series, check out the other previous videos. But yes, so that's pretty much how those operate. So reinforcement learning is pretty much, the concept is how we learn as humans. Let me give an example. So, right, so let's say my phone starts ringing an alarm, right? It's just ringing, and I want it to stop. I need to learn how to make it stop. Do I go like this to make it stop? Do I press a button? Do I press this button? Do I throw it? Right? So I try different things to figure out how to make it work. So when you get a new phone, you're kind of like, dang, how do I make this stop making sounds? You mess with it, and then something stops. You're like, okay. So next time it rings, whatever I did last time to make it stop, I'm going to do that again. But let's say it doesn't work. So it's like, oh shoot, like maybe that wasn't the right thing. Maybe you did something else, and now you're paying more attention to figure out what exactly it is that you did to make this thing stop ringing. Another example is punishment is another way to explain it. Or bad things happening. So like, let's say you're a baby and your mom says, don't touch the stove. You touch the stove, it burns you. Now you've learned, oh, don't touch stove, it burns you. The reinforcement was, don't touch stove. They told you don't touch it, but you touched it anyway, and that reinforced what they said is the correct thing to do, which is don't touch it, right? Reinforcement learning gives you two options, and you pick the better option based on what the goal of the situation is. If the goal is to not get burnt, right? The goal is not to get burnt. Are you gonna touch, or do you touch, or do you not touch, right? What gets to that goal? If you don't want to get burned, you don't touch. But you have to learn that by touching it, and then you realize, wow, which one's the better option? That's how reinforcement learning works. That's how agents operate. That's how robots operate, okay? The last one is policy gradient methods. The best way to explain this is just AI for robots and how they move and things like that, or how like their decision process essentially for doing actions and stuff is what policy gradient reinforcement is. But yeah, that's pretty much how that works. Yeah, pretty straightforward. Cool. So, but anywho, you guys, that is pretty much it for this video. If you guys want to learn AI from me one-on-one, if you want me to help you integrate AI into your business, if you want me to just, go over a concept with you, you have an idea you want to just ask is, hey, is this AI oriented? Is it good for AI? Whatever it is involving AI, email me below. My description is in the video description below. Yeah, I have a website down there as well. Check it out, you guys. But yes, guys, so don't be afraid to ask me any questions, and I appreciate you guys' time so much. Thank you guys so much. Peace.